our speaker today is Pulkit Agrawal. Pulkit's a graduate student in the EECS department. He spent a considerable amount of time with the Redwood Center and also with Jack Galant's group and with Jitendra Malik and Peter Veal, so he's sort of an out-and-out neuroscience and I guess more AI person. So he's been working on a bunch of really cool projects for the past year or so on both sensory motor representations and forecasting and predictions, and he's going to share some of his insights today with us.
All right. Yeah, thanks, Mayur. So let's get started. Right. So let's consider like a toy problem to begin with, and the toy problem is in a game of billiards. We are trying to apply a force on the white ball so that you hit the yellow ball in a fashion that it goes inside the pocket, right? So now a traditional reinforcement learning based setup would treat this problem in the following way. You apply a force on the white ball and the yellow ball ends inside the pocket, you get a reward of +1. And in case the ball does not end inside the pocket, you'll get a reward of -1. And with help of these rewards, you end up training a system which can now maybe hit this ball inside any given pocket, right? But now suppose I change the task slightly, and now my task is, instead of trying to put the ball inside the pocket, this ball is actually moving. And now I need to apply a force on this white ball so to actually hit this ball. Right, so I've changed the task definition only slightly. So in the standard reinforcement learning setup, I will need to retrain the system from scratch again, because the system has no representation of this new goal. Right, because it was only trained to hit this ball in a manner so it goes inside the pocket. Although there is this underlying physics which is consistent across both these tasks, our algorithms right now are not capable of transferring this knowledge. Right. So in contrast, we know that humans are able to kind of transfer a set of knowledge across tasks, while in reinforcement learning, this concept of transfer is something which people are very excited about and want to work on, but it's not there in the current algorithms. In contrast, if we consider computer vision, it's not the case. You have a lot of transfer happening from, say, you train your network on ImageNet, and then you learn some features which are then good for a wide suite of tasks. So how can we make transfer learning work in the context of reinforcement learning? Right, so in my view, there are at least two possibilities, none of which are exclusive. Okay, so first thing is maybe instead of training on just one task, which was very particular, like trying to hit the ball inside the pocket, we should train on a suite of different tasks. Right, for just like in the case of ImageNet, we were able to learn good features when we trained to classify 1,000 different classes. So maybe we also need to perform many different manipulation skills, and then we will learn a generic purpose manipulation system, which if given a new task can perform that very well. And a second phenomena, which is also important for planning, is the ability to forecast or to predict what will happen as a consequence of my action. Right? So maybe let's take a step back and try to think about these two things. So at least if we look at biology for a moment, then what we observe with infants is that they are kind of randomly playing around with toys. They kind of throw things, they push things, they bite things, and so on. It seems as if they are trying to like build a model of what would happen if I apply a certain action. Right? To us, it seems it's completely random, but it's an hypothesis that maybe when they are throwing this, they say, okay, I throw this like this, then I observe the consequences, and I'm training some kind of a model which is helping me predict what's going to happen next.
Pulkit, when you say consequences, you mean visual consequences?
You mean visual, yeah. Visual or through any sensory modality. You observe the consequences of your own actions. Right, so yeah, so maybe they're learning a model of how their actions are affecting these surroundings. Right? And if we go back to 1943, there's like this quote from Kenneth Crick, and I'll just read it because I think it's worth reading it at least once, that the organism carries a small-scale model of external reality and its own possible actions within its head. It is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, and utilize the knowledge of past in dealing with the present and the future. In a sense, what it means is, suppose if I can imagine what is the consequence of me applying a force on the ball. For example, let's go back to this scenario. if I can imagine the consequence of applying a force in this direction, or this direction, or this direction, in this direction, and I will know the ball will move like this, or like this, or like this, right? And then based on my imagination, I can imagine, okay, this ball is moving like this, and if I apply a force like this ball is going to move in this direction and they will collide. So this is the optimal force and not one of these forces. So if I have some kind of a model which can enable me to forecast the consequences of my action, then planning is kind of easy. Or not easy, but it's possible.
So are you taking a parameterized model, like the way you're thinking of a model, the way you're describing it feels parameterized?
So yeah, so I'll come to it. So there are two kind of models which you can kind of think of. One is an explicit physics model, where you can estimate some kind of parameters, such as what is the mass of the ball, and what is the density, or what is the friction coefficient, what is the force I'm applying, and then use your Newtonian physics to kind of infer where the how the ball will behave in the future. Right? That is one possibility. Second is what I am calling intuitive physics. It's not my word, it's a word being used in psychology for a very long time in the past. And what do I mean by these two terms? I'll just go over in the next slide, which is consider this problem of humans trying to catch a ball. Right? So one possibility is that you take the perception and the action problem separately, and what you might have an hypothesis that this human is actually trying to maybe estimate the mass of the ball, the air drag and wind direction, puts it into some kind of a physics simulator inside his head, and then computes the trajectory of the ball, and then based on that tries to run and catch the ball. So this is one possibility in which the model is completely parameterized by a few parameters such as mass or air drag. Right? A second possibility is that instead of doing these complex calculations, what one might be doing is that I am seeing this ball in my eye field, and I just move in a manner so that the location of the ball in my eye field remains constant. And if I do that, eventually I will end up catching the ball. Right? And this is what some researchers back in Oxford found in 1996, that people actually catch, or at least baseball players, when they're catching ball, they seem to be doing this kind of a behavior where they're holding the ball kind of constant in their eye field.
This was also something that J.J. Gibson pointed out in the 1950s of how you would know if you're colliding with an object.
Yeah.
Right?
Right.
What do you call it? Affordances.
Affordances.
Yeah, right.
Yeah. Yeah. Yeah.
You think that's a good question in calls?
What?
You think that's a favorite question in calls?
Yeah, so at least if we consider this example, what this is showing is that instead of trying to treat the perception problem separately, by perception problem I mean estimating the state of the system first, and then using the knowledge of explicit physics, which say Newtonian laws gives us, if we consider this joint problem, then we're able to find heuristics for certain tasks which allow us to perform these tasks in a much easier fashion. Right? And this is exactly what I am calling this intuitive physics. So without explicitly knowing about all parameters of the system, I have the ability to either perform the task or to forecast how things will evolve in the future. Right. So now let's try to see how can we actually build.
Sorry, I just want to have a mathematical understanding. So this intuitive physics is essentially the reparameterization of the. I think I can think of it as reparameterization, right? Because,
It is. Yeah, it is a reparameterization, but you are learning this parameterization. In the explicit physics, you will predefine a parameterization and say, my parameterization is mass and friction. And then you will try to build a perception system which tries to predict your mass and friction. And once you have that, then you will plug it into some kind of a model which will predict what will happen and then do inference.
Well, you could also learn that physics model too. Right? It doesn't have to be pre-specified. You can
So-
just watch the world and sort of infer these laws.
Yeah.
Right.
So that is exactly what I'm saying is intuitive physics in a way, because you don't have an explicit, you don't need to explicitly reason about the
That's
parameterization.
what I'm saying. It's just a third alternative. I could have the explicit physics kind of thing going on. I'm not saying that's happening.
Yeah.
You could have that going on and still learn it. Right. What you said is that you could have that explicit physics thing and it's predefined. Right. And then you have your intuitive thing, which is not even, it's not explicitly parameterized as
Yeah.
learned.
Yeah.
Right.
Yeah, so I guess what you're saying is that instead of predefining the physics engine, you can also learn the physics engine, but have the interface be predefined. Is that what you're suggesting?
Oh, it's all right. existing.
Yeah.
Like you can have a notion of gravity, but you might not know how gravity actually works, and then you learn how that works based on your visual system, which would be somewhere in between these two sets of.
Yeah. Yeah.
But when you say keeping I field constant, that's the parameterization. The space of intuitions are also huge.
Yeah. Yeah.
So there is no way to, you have to constrain, you have to parameterize.
No, you have to parameterize, but you cannot define what the parameterization is a priori, right? So, for example, suppose that if I am observing, so suppose my task is to predict the trajectory of ball in the future, right? Or maybe let's consider a second example, okay? Let's consider that I am throwing two objects from top of a tower. One is a feather and one is a stone, right? So, and I want to predict which one of them is going to fall first on the ground. So now there are two possibilities. Either I say I'm going to estimate again the mass and the air drag, and based on that I'm going to compute which of them is going to fall the first. That's one possibility. Second, I can just look at the texture of the feather and the stone and have a think that things which have feather-like texture tend to fall more slowly, because this is what I can observe in the world around me, right? So now the question is, which of these models are going to be better at predicting the outcome of my action, right? So now it depends on if you are using some perception system. It depends whether it is able to detect texture more robustly, or it is able to estimate, say, air drag and mass more robustly. So depending on that, you will want to choose one of them, but you don't know a priori which one of them is going to be better. So what you do is you just observe this event happening multiple times, and then you try to build a model which takes in, say, your visual images and tries to forecast how the feather will fall and how the ball is going to fall. And then based on that, and that basically becomes your model at the end of the day. Does that make sense? Or?
Yeah, it makes more sense. But but my question is, if you want to learn like a statistics of images, you
Yeah.
can go and learn features, right?
Yeah. Yeah.
So the way I want to understand this action, in the action world, there are also features in the action world, right?
Yeah.
The space of possible actions.
Yeah.
So, but it's not phrased like, you are not actually going to learn, for in the example of catching a ball.
Yeah.
This could be, I feel it could be, the space of possible actions is huge, right?
It's huge, yeah.
But the problem is action. When you think about actions, you have to, for any specific problem, you have to think, so what are possible actions?
Yeah.
And this for me is a parameterization. When you do ImageNet, you don't, you are not, or when you're learning the statistics of images, completely, you don't have any prior. You have some prior, but
yeah.
I
So
feel it's
so
more,
so over here, what I'm saying is, so suppose even you fix the parameterization of your actions for now, but you still want to forecast what will happen when you apply an action. So for each parameterization of an action, which could be I want to move my hand forward, or if I apply a force in this direction, or if I just like pick something up. So given what is the state of the world right now and a parameterization of the action, how will the world be in the future? So the problem is not saying try to come up with an action parameterization. I'm saying assume an action parameterization and the current state, and I'm just trying to say what is going to happen next.
okay.
Yeah.
So at the end of the day, you have a parameterization
Of the action,
of the action.
but not of the world state. I am not parameterizing the world in terms of physical parameters for now. Yeah.
But isn't that a constraint? You're parameterizing action world, right? Well, action is part of the world, basically.
No, action is what you perform in the world, right? It's the agent.
Yeah, but you are parameterizing. You're not learning to me is also learning the possible actions. When you're parameterizing, you're constrained, basically.
So you can perform all kinds of random actions. So I'll come to it later. Okay. So maybe if that question is not answered, we can revisit it in some time. Yeah. So so we talked about we want to build this model of the world, right? And then in the model of the world, there are two kinds of model you can build. One is the model of the environment. By that, what I mean is if I apply a force, then objects on the table are going to move. So what is the effect of my force on objects in the environment? Second is the model of the agent itself, that how will my hand move if I apply some force? Just to make this distinction clear, let's again come back to running example of billiards. So the model of the world is going to tell me what is the force I need to apply so maybe hit this yellow ball so it goes inside the pocket. This is basically your knowledge of physics, which comes into play, which helps you infer this force. Second is how to actually apply the force on this ball, which is the second thing you need to do. This is where you're dealing with how should I move my hand so I can actually apply a force which I'd inferred through the model of the environment. So there are two distinct models which one can think about. And if you think about this a little bit more, you can kind of safely assume that the agent itself is not changing over time. Like my hands and my legs are not changing substantially over time. But the world is changing over time all the time because I'm going into new environments, into new situations, and this kind of makes the problem of modeling the environment maybe a bit harder than trying to model the agent itself. Does this make sense or not really?
So one's a forward model, one's the inverse model.
None of them is inverse. These both are forward models. One is saying that suppose if I want to apply a certain force on the remote, then how do I move my hand, right? So, or in the sense, if I apply these set of commands to my different muscles, then how is my hand going to move?
Oh, I see. So there's two forward models. One's of the environment, and one's of your own actual.
Own actual actuators.
Yeah.
Right. And one of the central problem, if we try to make predictions, is what is a good feature space to make predictions in, right? So what I mean by this is, should I predict how is the world going to be at the next state by trying to match the image exactly? Or do I come up with some kind of a parameterization that I need to predict? Like what is that parameterization which is good to forecast in the future, right? So let's consider some possible instantiations of it. So option one is that suppose I am again interested in predicting how are these balls going to move, right? And what I can do is I can train some kind of a neural network to output some kind of a fixed parameterization of the world, which could be I want to output the velocity, right? But I'm not choosing what features I am using to predict the velocity, but I'm choosing what is the world state I am trying to predict. Right? So this is like one possible choice which one could make. And if you end up making this choice, you can get reasonable models. So what I'm showing you over here is that this neural network which I showed you takes as input this current frame and the applied force and tries to forecast where this ball is actually going to be in the future. Oops, what happened? Uh-oh. Seems my video is not working.
You haven't saved someone?
It should be working. Wait. Oh man. Uh-oh. Why is this happening? 1 second. Let me pull up my, I don't know. I was trying to check if my other videos are also not working.
You might play in that mode. Oh yeah.
No.
No.
I'm saying media not
Oh.
No, just, yeah, just give me 1 second. I'll just try to see what's happening with these videos. So maybe this is how like the forecasting of that model looks like, right? So if you take the state representation, then you can end up getting like a reasonable forecast of how this ball would move, which is pretty simplistic, but it's just like a sanity check that this thing can actually work. So Okay, you'll have to take my word for it that this model also kind of works, and even if you have like 3 balls, they kind of move together. And it's not perfect, but they tend to behave in the way that you can collide and so on.
Sorry, could you just explain that again, what you just showed? What does that show?
So what this shows is that if somehow someone magically came and told me that the right thing to represent the world in the future is predefined, and I predefine it in terms of velocity of the ball, and then I just takes in some images and try to build a model which says, okay, given the image right now and the force that I'm applying, how will the ball behave in the future? So that is the model's forecast. So I'm generating the imagination of the model by giving in this frame and the force that you apply. Right, so that makes sense or no? So the input to the system becomes like this image and the force.
Input to the neural network.
Yeah.
It's perceiving this system. It's looking at this whole thing.
Yeah.
Okay.
So the neural network takes in this image.
Good. Okay.
And then the force that you're applying.
Got it. Okay.
And then tries to output where will the ball go next. And then what I'm trying to show is that you can model things like collisions just by training a system to predict the ball velocity. So you don't have to explicitly define that there are walls or there are other balls in the environment just by looking at the trajectories of how the ball is moving.
So it learns what that red line means.
Yeah.
And when it hits it, it's going to bounce off this way.
Yeah.
And now you showed basically now after you train it, you're
Yeah.
just showing
Yeah.
the simulation of that dynamics, of
Yeah.
that learned dynamics.
Yeah, the learned dynamics, yeah.
For arbitrary scenarios.
For arbitrary, yeah. Yeah.
Seen before.
Yeah, so you randomly generate these different wall configurations and different number of balls. So in this scenario, they were like the system was trained on 2 balls, and then we test on 3 balls, which it has never seen, and then you try to show generalization to those kind of scenarios. So it does.
Like, does it also generalize with like the thickness of the wall and the color of the wall and things like that?
Yeah. So like for example, in 2 to 3 walls, if I could show this video, you would see that the collisions are not perfectly like elastic, and you have some kind of like thing where they don't go very smoothly, but they still kind of come together and then they go apart and so on.
So just to be clear, the image, in the first case the video that you showed, those were images generated by the network in terms of.
So the network is not generating the image.
It is giving the velocity.
It is giving the velocities
Okay.
by which you are simulating.
So then it doesn't have to predict like movement and hitting off the wall and stuff like that, because those are things that exist in the wall in the system.
No. So you're not.
Velocities will change in it.
The velocities will change, right? So you can think of like the generator is fixed right now. It
Like a
takes.
rendering engine.
It's a rendering engine. To the rendering engine, you give the velocity and it renders the world in the state.
So the first example here, there's the velocity
The
of
velocity
that ball.
of that
So
ball.
we have 3 balls.
Yeah,
There are 3 velocities.
the 3 velocities.
So how do you parameterize that up here?
So the way we train the system is that you consider the system can track the ball. So there's a glimpse around the ball, and the glimpse outputs the velocity of the ball on which the glimpse
That
is.
you're currently tracking.
That you're currently
ignoring the other 2 at that time.
So if they're inside the glimpse, then their effects would be accounted for.
But now if they're both inside the glimpse, now we have 2 velocities
No, you only predict the one which is at the center of your
in the
glimpse.
center.
Yeah, you only predict for that one. Yeah, and then you do it for all the balls, and this
By moving the glimpse to
by moving the glimpse to different
So
balls.
when you reproject it, what if it's like a impossible configuration, right? Because I mean, if they predict the project velocity is slightly wrong, then 2 balls may be trucking on top of each other.
What? Like if the 2 balls end up exactly on top of each other?
Well, yeah, because you're saying you're predicting each ball independent, like sort of separately, right? You're generating a trajectory for each ball.
Yeah,
There's
but
configurations where it's not possible for them to both be in the same position. Right?
and you are predicting them independently, but you account for other balls also, because if you're seeing the other ball, then you will account for that ball's motion.
Right, but I'm saying when you regenerate the image
Yeah,
and you actually show, like, let's say they bounce too early.
yeah,
And they just like sort of like never touch.
yeah. So they will never touch, and they will just kind of come close
Yeah.
and then move apart. So it won't be physically realistic. It might not be always be physically realistic. Right. And this is just kind of, again, visualizing this, but in terms of heat map. This is showing the initial position. The arrow is the force, and dark blue is the start of the trajectory, and light blue is like as you unroll in time. So what you would see is that the kind of collisions look realistic, but the trajectories might not exactly be the same. For example, over here, right? So over here, the model kind of drifts. It predicts something like this. The actual ground truth goes like this. So there are some differences, but overall it gets this basic idea of that I have to collide with the balls, with other balls, kind of correct, right? But over here, we made a very central assumption that we knew what was the right thing to predict, which was the velocity. Now, this is not necessarily true in all prediction problems. We don't know this, right? So one thing you could do is that I take in my current image, encode it into some kind of a feature space. I have some action, and I also encode this into some kind of a feature space. And based on these feature representations, I try to output some encoding from which I can decode the next image, right? This is saying, okay, I am just going to generate the image which will happen if I apply a certain force, right? But we all know that generating images is kind of a hard problem, right? There is a lot of exciting work, like on adversarial networks and stuff, but I guess the question is predicting pixels even the right thing to do, or do we want to predict something else, right? So,
can you go back? What do you mean by action encoder?
What I mean by action encoder?
Yeah, so it's,
So what I mean is that you take your action,
yeah.
which could be, say, the commands that you apply to your motors.
Or in the Ilya Ball's case, that's the
Very-
force.
Is a force, yeah.
It's just very few
It's-
parameters, right?
it's a few
Encoding
parameters.
it, it's
So-
already that's encoded.
So you project it into a high dimensional space. And the reason you want to do that is that maybe your computation is much more linear if you project a low dimensional space into a high dimensional space. Right?
Even if it's a one-dimensional scalar, how would you put that in high-dimensional space?
Yeah.
You just multiply
You
Just
just multiply by a matrix, which projects it into a high dimensional space. Yeah.
It has like the same contribution in different.
Yeah. Yeah.
Okay.
And it's the same way that, okay, if you have image, you understand encoding because you're saying it's a compression which is happening over here, and therefore it makes sense to you in case of images, right? But essentially, why you want to do this encoding is because you're trying to find a feature representation in which, if I have the image and if I have the action and they interact, then it is easy for me to output the next image, right? So it is not necessary that your low dimensional representation is the optimal one, because the manifold of the next images might be highly nonlinear in that. But maybe if you project this into some kind of a feature space, learning this mapping becomes much easier. That's all this is saying.
Yeah. But what's the learning? I mean, there is a learning when we code images.
Yeah.
They have some principles.
Mm-hmm.
How are you encoding actions? You didn't explain that, right? I mean,
Yeah. So
how do you put it in a high dimension, a single number in the case of force, for example?
So in the case of force, for example, you have your fx and fy, which could be, say, force in x direction and force in y direction,
Yeah.
which is a two-dimensional number, okay? And then you suppose you put a matrix which is 2 cross 100.
Yeah.
So that puts it in a 100-dimensional space, right?
Is that just random or is it learned?
It is learned.
Oh.
You learn it.
Okay. So you start at random and then it actually
Yeah.
tweak with it.
Yeah, you tweak with it. You start, so all of these things are learned,
Okay.
right? So for example, in case of this thing, your loss would be, is how accurate is my reconstruction, and then you backpropagate this loss, and then you learn this encoding, and then you learn this encoding. So you're trying to say what is a good representation of the action so I can actually predict this particular image. And then you're trying to learn this mapping.
So why do you think, can you give us some intuition, why do you think a 1,000-dimension representation of a two force is a good representation?
And so the simple example is, suppose,
For images, we all understand it, but what is it for actions?
so if you have, say, it's like the same motivation people have for the kernel trick, right? In the kernel trick, the motivation is that if something is very nonlinear, if you apply a kernel and you go to a space which is high dimensional enough, everything becomes linear.
I
Right.
understand actions on images creates nonlinear actions on images. So
Yeah.
images, the transformation in images is highly nonlinear.
Yeah.
But what about actions themselves? Are actions themselves nonlinear?
So the effect of actions on images is nonlinear.
Sure, yeah.
So you're just trying to project both. So you combine both of them over here, right? So you make some encoding to say 2 to 100. You have some image encoding. You combine them, and then you put more layers on top, right? So in that way, you're taking this whole transformation and trying to project it into a higher dimensional space.
Okay.
Right. So, okay, so the question you were like, okay, is images the right thing to actually predict, right? Or do we want to get something else? Right, so maybe let's consider this example where I'm showing you like image of some trees in the autumn, right? And if I ask you, there's the ground, and what would be there on the ground if it is autumn? There would be leaves, right? So, but if I ask you, can you draw where is each leaf going to be on this ground? I just maybe try to run that mental simulation, right? So what you would find is that it is easy to predict that there are going to be leaves on the ground, but it is very hard to predict where exactly these leaves are going to be, right? So it's like different feature abstractions allow you to make different kinds of predictions, right? So essentially, if you want to make such predictions, we don't want to predict exact pixels, but we want to learn some kind of an abstract feature space in which we can forecast what's going to happen.
Well, another way to say that is like you want to learn a distribution of images, right? There's not just one image.
Yeah.
Right? There's a bazillion different images that could all fall within that class. And
Yeah.
So you can imagine having some. That's like the Karkland-Lewicki model. Kind
Yeah.
of works that way.
Yeah.
We're modeling a distribution of our images rather
Yeah.
than that image.
Yeah,
Right?
and
Which is
that.
a lot more reasonable.
Yeah.
In many cases.
Yeah, and that is why, so you can think of it as instead of again modeling the pixel distribution of the pixels, you can model distribution over some latent representation of pixels. And that's, yeah.
So basically you're measuring the distance between a prediction and the actual signal by some statistics.
I'm not doing that right now. I'm just trying to say, like, that instead of trying to just regress onto the image, that probably is not the best idea because you don't exactly know what's going to happen next, right? You can say at a very high level that, okay, there will be leaves. But exactly if I ask you where the leaf is going to be, you probably even don't care about that, right? You're only interested in saying, okay, there are leaves, but I really don't care where those leaves are for many tasks that we perform, right? So maybe we should use neural networks to make predictions in some kind of an abstract space and then see what happens if we try to do that instead of trying to regenerate the image. Right, so one simple way you can kind of formulate this problem is you again take the image, your action, and you build a predictor, but instead of trying to now predict the image, what you do is you encode this image into some feature space and you try to minimize the loss in this particular feature space. Right, so you can think of this encoder might try to map different configuration of leaves into the same point in the feature space, and this might work out, right? But this thing has a trivial solution. Okay, this formulation has a trivial solution. Like, do you guys see what the trivial solution might be to this? Yeah. So if I set the encoding of z's to 0 and v's to 0, then this is trivially satisfied, right? This losses go down to 0, and there's no learning which is going to happen. Yeah.
So what if you have some statistics and you try to maximize the entropy, right? You try to choose the most random distribution rather than the most constant distribution.
And so you have a trade-off, right? You want to also predict what is going to happen next. So if you make it too random, then you can't really predict. But anyways, you can put some kind of regularizers. You can say, okay, my z's do not need to have norm 1. For example, I can put that regularizer over here, and then I can hope something would happen. But it would be very, very hopeful that I'm putting some regularizer which is not necessarily helping me make forecasting, but I'm somehow hoping that would help me forecast. Right. So now at least this way of doing things is not going to work. So maybe let's.
Can you say again what's this abstract space? From predictor, you project it to another space, which is Z. Is that the?
Yeah.
Is it linear projection?
No, it's a nonlinear projection.
Nonlinear projection.
Through like
Z.
yeah.
Like Z.
Yeah, through like multiple layers, it's a nonlinear projection. Yeah.
What's in that horizontal predictor box is a.
So this is again
It's a multi-layer.
it's a multi-layer neural network sitting
No,
over.
from predictor to Z. That's my question.
So you take ZT and VT,
Yeah.
feed it into a nonlinear neural network.
Oh,
Which
that predictor is a
Yeah.
box is very.
Yeah. Yes, I'm kind of hiding some details
How
over
about
there.
from image encoder to Z, that's Z hat. Z hat. How about-
Z.
Z, this one.
Oh, I see.
So this is again, you have a convolutional network, say 3 layers convolutional network, then 2 fully connected layers. It's a 5-dimensional neural network sitting over here, which encodes this image into ZT plus 1.
It's a bunch of magic neural network boxes.
It's like, yeah,
So
those are neural network boxes.
yeah, right, exactly.
Yeah, maybe I should have drawn, in one side I should have maybe explained
Yeah, yeah.
the neural network. Oh yeah. So okay, so we are stuck. So now let's try to again take a step back and see, okay, how can we fix this problem? Okay. So as humans, one thing that we're interested in is, suppose I'm holding, say, a bowl of glass with me, and then I drop the glass. Okay. So what I'm going to see is this, right? So I am not really interested in saying where all these small pieces of glasses go, but what I'm really interested is if I give you this image and the previous image, what is the action which led from the current image to the next image, right? If I know that, then I'll be able to act in the world. So if I say this is the goal state that you want to reach, and I specify you an image of that, and I have the current image, I just require the sequence of actions to go from the current image to my goal image. That is all that we're interested in terms of performing actions.
What about textures and fabrics?
What?
Texture. So you don't exactly need to know where the pieces are, but you probably can synthesize this texture and just a fractured glass, right? Just like you stack it in Mumford and Drew's paper predicted the texture.
So you can predict the texture statistics of this.
Yeah.
That is possible. So then again, you have to then define for every scenario what is a good statistic. So in this case, you can say it's texture statistics. Maybe texture statistics will not be interesting if I'm trying to say rotate this object. Because if I rotate it, the texture is probably not changing, but then I cannot predict the outcome of my forces, right? So then you will run into that issue if you do that, right? So, okay, so let's maybe try to do the thing that we talked about, which is we have our image over here, which is my current image. This is the image which I actually want to reach to, which is my goal image, which someone specified. I can then again do the magic neural network boxes and go to some latent encoding, and then try to predict what is the action that will take me from this image to this image, right? And then I can train this system up, right? And this is classically known in control as inverse models. So the first model I talked about were forward models, because they say given the state and the action, what will happen next, which is you are rolling the world forward. This is saying image and the next image, what is the action which transforms it? This is the inverse model.
Right. I mean, going back to your previous scenario, you see the problem with that is that there's a trivial solution.
Yeah.
But isn't there a trivial way to fix that trivial solution?
And that would be?
Well, what about Becker and Hinton? I mean, what you're doing here shares a lot of similarity to what they did. I mean, like, for example, the idea of mutual formation.
Mm-hmm.
Right? So if you say, I want to maximize the mutual formation between these two, then now that's going to encourage each of those to have high entropy, right? So it's going to avoid the trivial solution, because if you're just pegged at zero, that has zero entropy, you're not doing anything.
Yeah.
But if you instead formulate mutual formation as the thing you want to maximize between, instead of squared error, right? Because if you just do squared error, you have the trivial solution. But now if you say, look, I want this variable to have high variance, and I want this variable to have high variance, and I want them to match.
Yeah.
Right. That's kind of what mutual formation is going to be doing.
Yeah, but that is also, it would make it like kind of very hopeful also in some sense, right? Because you're essentially trying to maximize the variance of each of those variables and try to say these are going to be as random as possible, but let me try to match them also.
Well, that's what you want to do, right?
And but the thing is, you don't want them to be random, totally be random, right?
Well, not random. I mean, they're deterministic functions of the input, but they just have variance. The idea is, you're just saying, I don't want the zero solution.
I guess it's no guarantee that it will run the right representation for you, even if it has high variance and matches the two. There's a lot of trivial solutions.
Well, that's a different problem, but I guess you're sort of, it seems like you're Xing that out because you're saying there's this trivial solution, and now we can fix that trivial solution. Now you're saying there's another problem with it.
So maybe let me go through a couple of slides and let us revisit that discussion.
I just want to make a quick comment on that.
Yeah.
So maybe not just only marrying the variance, right? So you can take several linear functionals of this distributions and then still maximize the random
Yeah.
The more you take, the more statistics you take, the less, the more you constrain the space
Yeah.
of the possible functions, right? And then in that case, you're trying to find the most random function, which will be significantly constrained when you have more statistics. Maybe not just the variance, but you can have several other statistics. Not too many, but maybe 3.
Yeah.
4 something.
So okay, let me address this question in just 3 or 4 slides, and then we can redo the discussion. Okay. So let us see what happens if we end up training this system up, right? So what this will help me train is a feature representation which is very, very specific to this particular task. And the task is that if I have this image, the current image, and the next image, what is the action I need to perform? So this will help me learn a feature representation which is specific to the tasks I need to perform because I'm optimizing for it in this framework, right? And then if we just take a step back and let's kind of contrast the forward models and inverse models we talked about. In forward models, we had this thing that predicting pixels was hard. But in inverse models, predicting actions is easier. This is because actions are much lower dimensional, so modeling them is probably easier. In the forward models, inferring controls again becomes non-trivial because you have your image, and then you have to run some inference procedure to infer your action from this model. Whereas in the inverse model, controls are directly outputted. You take the image, the current image, the goal image, and you directly output what is the control I want to apply. But there's also one more thing. In the forward models are kind of more nicer in some ways because if I have the current state and if I apply an action, there's going to be one consequence which is going to be there. In case of inverse models, this is not true. For example, if I want to move this to here, I can move it like this, I can move it like this, I can move it like this. So there are multiple possible solutions of how I can go from image 1 to image 2. Right? So it seems like maybe the forward models can provide some kind of a good inductive bias because given the image and the action, there's one possible future, whereas inverse models have some of the properties that we care about also, or which makes the modeling easier. So if we now try to combine both the forward and the inverse model, how this would look like is we again have, this is the inverse model we talked about before. We take the current image, next image, try to predict the action. Right? And then I take my action encoded. This was my latent representation of my image, which I put over here again. And from the representation of my image and my action, I try to predict the next state. Right? Which is saying this is my current image. I encode it to some feature vector. This was my next image encoded to some feature vector. These two feature vectors should predict what was the action which transformed this image from this. And now I also say that from this ZT and VT, I should be able to predict my ZT plus 1, which is saying I'm trying to do the forward dynamics, but in the Z space. Right? And the way you do this is by trying to minimize this loss. Does this make sense?
Yeah, it's much more intuitive.
Yeah. So what is happening over here is that you're learning a task-specific feature space over here by training the inverse model, and now you're unrolling the dynamics in this task-specific feature space. Right? So this is what this framework is allowing you to do. Right? So now let's maybe revisit the discussion we were having before of trying to do this mutual information. Right? I think the difference between those two frameworks is that over here, you're saying there's a task which I am eventually interested in performing, which is I want to perform actions in the world, and I'm training a feature space for that task, and I'm unrolling my dynamics in that thing, in that feature space. In the mutual information, I can still do dynamics in that space which I learn, but I have no guarantees that this space, how good is this space for like inferring actions. Right? So I think that is, so the mutual information in theory could work and provide that.
Well, I guess I'm just trying to follow that. Like, the logical change, like if you go back to the previous slide,
Yeah.
You're saying that the previous one.
This one?
No, yeah, forward models. You're saying so predicting pixels is hard.
Yeah.
But you have a solution to that, which is to do this in the latent space.
Yeah.
Right.
Yeah. So
So it sounds like I mean, the goal, what you want to do is infer controls, right?
Yeah.
And so I think So it seems like the problem isn't that predicting pixels is hard because
Yeah.
you can do something on latent space. And
Yeah.
so that's you've solved that problem. But now
Yeah.
you're saying that the forward models are still bad because not optimal because inferring controls is
Yeah,
a hard problem.
because inferring control is not still. So the thing is, so you have solved this problem by going to a feature space, and in that feature space, you're trying to make predictions, right? So now, can we make this feature space have the characteristic that it will be good for inferring the control? If that is true, then I will solve all of these three problems. So the mutual information thing is not helping in this, because the mutual information nowhere says that the control problem should be easy, or should be.
I think all Bruno is saying is that the statement that you're saying about predicting pixels is hard
Yeah,
is not necessarily fitting in with the rest of. In that, like you have a model of predicting pixels by using an autoencoder or something where you go to a latent space
Yeah.
and then you're able to generate. So you can predict pixels and you are predicting pixels even in.
No, he's not predicting pixels.
Well, implicitly in the latent space, right?
Predicting latent space. not
Yeah.
predicting-
yeah,
I see. But it's just it sounded like the beginning like what you wanted to do was predict the image, and then it was like, well, but you really want the whole goal here is I guess I wasn't getting the whole goal is you want to be able to go back and infer.
So the whole so I guess the whole goal is you want to be able to infer the actions, and the mutual information prior will solve this and this, and I guess it should be experimentally tested, like how well it will perform for control.
So can you? Sorry, go ahead.
Yeah.
I have a question on the last slide you showed.
This one.
Yeah, so this one, I just want to understand. So the the action space, as you said, there are many action spaces, right?
Yeah.
That leads to the same transformation.
Yeah.
So I feel, maybe I don't understand this image. So it feels like Z hat has a different distribution than Z in this way, isn't it? So what is Z? Z hat I understand. What is Z again?
So Z is the encoding of your
ZT plus 1, sorry.
ZT plus 1 is the encoding of your next image. Right. So you have your current.
Encoding of next image, but so Z hat is the encoding of action and Z is the encoding
No, so
of image.
Z hat is a prediction. All the hats are predictions. And
Yeah, but
Z.
it comes from the action space. There is no image in Z hat, right?
No, this is ZT, right? So this ZT is coming just from over here.
No, you're minimizing ZT plus 1 minus Z hat T plus 1, right?
And you're minimizing this, and you're also trying to predict the action accurately.
I guess my question is, when you're drawing in this diagram of Z hat, there is no image.
There's no image, yeah.
Yeah, so
There's no
it
image.
comes from just action.
No, Z is the encoding of the image.
No, Z hat.
Z hat is the predicted encoding of the image.
So the next image.
So ZT,
This picture you're showing is
so,
just,
so this is ZT plus 1,
yeah,
right? Now this picture is showing you encode the action,
yeah.
you have ZT. Now this ZT is coming over here.
So why is it going out the left and coming on the right?
Oh, it's actually like something like straddle.
Because I really, the slide, I think it's a visualization thing.
There's no time.
There's no time.
circularity or whatever.
No, this is just showing this it is the same
You
thing.
just saw
over-
it going from, you just didn't want to cross screen.
Yeah, I just didn't want to cross it like this.
It goes from here and then
got
it
it.
comes down here.
Okay.
Yeah.
Right, so you combine VT and ZT.
So you combine your latent encoding of your action and the image, which tries to predict the latent encoding of the next image.
I guess what I think, the way I understand it, you're matching forward model and inverse model, right?
Yeah.
That's how you think about it?
Yeah.
Yeah, so in your last, comparing forward model and last model, there was like they were very distinct, right?
Yeah.
So I feel like the distributions also show up in the distribution. If you go back to the slide you showed to Bruno.
This one?
Yeah, exactly. So the last part,
Yeah.
that's my question on the last part.
Yeah. So this is okay. So this is saying that if you are having a forward model, they could provide you a good inductive bias, right? And the reason I am trying to say this is because if I have the current state and if I perform an action, what would happen next? I know it, and because I can observe the world, and that is kind of known. In case of an inverse model, there could be like multiple ways of doing the thing, which makes the learning harder, right? So if I have the
Where does it show up in your model? This has to show up in your modeling, right? It shows up in Z hat, and the description of Z hat is
Like what?
This point that you
So,
made,
so this will show up in your z's. So your z's will behave in a nicer way because you're doing the dynamics in z now.
You have a, is UT, they're not the same actions, are they? Do you also have a cost on UT and maybe UT
Yeah,
hat?
yeah,
Okay.
yeah. There's a cost over there. Yeah.
So the reason why you don't want to do this in a single model is just because inference could be expensive in terms of the optimization.
For what thing?
The optimization, so like instead of having an action predictor and an next state predictor, you could have a next state predictor only
Yeah.
and just do like similar to sparse splitting, we optimize for the z variable and do a mean squared error after we've optimized and then scrap properly. Yeah.
So then you will have to use something like mutual information first to hold that space from not collapsing.
But you can still also regress on the action too, the ground truth action that actually generated that too.
No, but then you will again have a trivial solution. We can discuss that
Okay.
because your z will encode your a in some ways.
Okay.
That's yeah. So how much is it? Like already one, I guess. What?
Fine, keep going.
Those who have to leave. We've been interrupting you, so just go ahead.
Yeah.
You should take as much.
Okay. So I'll maybe try to wrap up in like 15 minutes or so.
Oh, okay.
Yeah, the videos. Sure. Okay, so now, so what was the takeaway we have right now is that, okay, if we combine the inverse and forward models, we can learn a feature space which is specific to the task that we want to perform, and then we can unroll the dynamics in that particular feature space, right? So that is what the framework that we talked about right now is kind of buying us. And why we started off this was because we posed the problem initially, okay, what is a good feature space to make predictions in? A good feature space to make predictions in is the feature space from which I can do control, because that's what I am interested in. And this is kind of giving you a framework to learn a feature space which is specific to the problem at hand and also unroll future. Right? So now one task which we might want a robot to perform is, okay, I give you this initial state of the world, and this is my final state in which I've just rearranged these objects. And given these two objects, I just want the robot to output a trajectory of actions which lead you from this image to this image. And this is like one task which our robots are not even close to performing, but would be a fun task if they could perform this one.
It's awesome. That's this reinforcement learning book, right?
This is a reinforcement learning book, yeah. Right, and this is what we were kind of considering in our recent paper, which we call Learning to Poke by Poking. So then this is joint work with Ashwin, who's an undergrad, Peter, Jitendra, and Sergey. And okay, my video will, I think, again not play. So I'm going to load this video. Just kind of 1 second. Yeah, I'm really not sure why my videos are not playing. They were playing just before I came here. 1 second. Okay.
Mine hasn't forced you to do Google Slides.
What?
You haven't been using Google Slides when you do DMS.
Cool. Yes. So this was the robot setup and that we had. Now, okay, instead of having those multiple objects, we have one object to start off with. And then the robot, what it does is, it like pokes these objects like randomly. So it comes, it sees an image, it applies action, and it sees like the next image, right? So this is kind of similar to object, action, object, and then it keeps on observing these interactions. Okay. And over here, the actions it is taking are almost random, but they're biased in a way that they will always hit the object. Other than that, there's no prior on.
And it's like three-dimensional
So-
force, basically.
Yeah, it's a three-dimensional force, but it is.
So you
But
start in your UT, you start with just three numbers.
Yeah,
And then
yeah.
project it. I see.
yeah. Right. So now this is just showing why even this problem could be hard, because of these kind of nonlinear interactions which happen because of the contacts between these objects. So first we collect like this data for a long period of time, which is approximately like 50,000 data points, which took us around like a month of robot's time, like running this experiment.
Overnight doing this stuff, or
Yeah, so robot runs on its own.
you don't have to watch it or
No, not at right now. Like initially we had to like babysit the robot, but right now we don't have to babysit the robot. So it can now kind of work on its own, right? And now I'll go back to my PowerPoint and we can follow from there. Sorry for this. So I'll just skip where we were. Uh-oh.
Just scroll before you start.
Just scroll.
Yeah. And then click the slide you want and then.
Yep. Okay, so this was the robot setup, and then we are back to the thing that the robot sees this before image, after image, and then predicts this model predict the poke, and everything else remains the same. Right? So now let me describe you how the robot is actually performing this poke. Is at the time of data collection, we assume that the robot has access to a point cloud, so that it can actually choose a point on the object. So it randomly chooses one point on the object where to poke to, right? And then it restricts its hands to move in a plane, and it tries to choose a direction in which it wants to apply a poke. So it could choose any of those directions. It randomly fixes a direction, and then how much or what length it should poke for, right? So it chooses the length and then actually executes the poke. So the hand will start over here, hit the object and go over there. So the process is you choose a point, you say what is the angle in which I want to poke and how much I want to poke.
How does it determine the point on the object? Like that is.
So because
it knows the object, like what?
So you have access to point cloud for just choosing the point on the object, for nothing else, but you use the point cloud for that. Right. And okay, so I had a video which I am going to skip. It's basically showing the hand will come over here and sweep it over there. Right. And with this parameterization, and then the parameterization becomes the position of the object, or the position of the poke, the angle of the poke, and the length of the poke. Right. And then we take the framework we talked about, and this is like the more neural network way of seeing the same framework, that you have your images, pass them through some convolution layers to get some feature encoding.
That was the Z before.
The X is the Z before now. And then you have action. And this action and your XT, predict your XT plus 1, and you're also predicting the poke. And then you train this system like jointly. Okay. So now how do we actually use this model to perform control? By performing control, I mean I give you a goal image which I want to achieve, and I start with the initial image, and I want to output a sequence of actions. Right. So I use the inverse model, which gives the initial image, the goal image, what is the action. Then you actually execute the action. Instead of reaching the goal image, you might end up somewhere else, which is not your goal image. Then you feed this back in, and then you keep on iterating this process. Right. This is how the model is run. And the next question comes is, okay, when do you actually stop? Right. So when we did a couple of things. The first thing we did was like first poke, which is you only stop after the first poke. Or you have an oracle which tells you when to stop, or the model predicts when to stop. And this prediction is based on the fact that you can compare your Z feature space and say the distance is small enough, I'm going to stop now. So those are three things. So these basically act as baselines for this. Or this is like the best you can do, and the first poke is a baseline saying, if I just stop versus doing a sequence, does doing a sequence buy me something more or not? Right. So one point to note is that although we train the model for single-step prediction, we are actually using it in a multi-step manner when we are trying to actually perform actions. So how well does all of this work? So first we did some simulation experiments, then I'll show you the results of the experiments on the robot. Simulation because you can vary things a lot more and draw some conclusions faster. So this is showing, the image is showing you like 4 different random examples. The task over there is there's a rectangle which can rotate and translate in a 2-dimensional plane, and you can apply forces. And you want to reach this target image, and you start off with this initial image. And this is showing the predicted forces by the model as it tries to transform the initial image into the target image. Right. And the plot over here is showing, the x-axis is showing the number of steps, and the y-axis is showing the error between the target image and the final image. And the error over here is measured as the distance between the objects and the location of the centroid of this with the centroid of the target.
Wait, what is it?
The number of steps. So step 1, step 2, step 3, step 4. So for each step, what is the error that you mentioned, right? So first thing that you will just notice is that as you increase the number of steps, the error is actually reducing, which kind of says that, okay, even if you train for 1 step, if you use for multiple steps, it is actually helping us. Okay, second is what we did was, we trained the model with different amounts of data. So you can train with say only 10,000 data points, 20,000 or 100,000. And we trained both the joint model and the inverse model. So the inverse model only is shown in dotted lines, and the joint model is shown in solid lines. So what you would observe is then the amount of data is less. Like training the joint model is like forward plus inverse both. That is the joint model. And the inverse model is only training the action and not doing the dynamics. So what you find is in the low data regime, having the joint model is better than the inverse model, right? And this is exactly what happens if something is a regularizer. That if you are with less data, you tend to perform better, right? So the motivation that we started off with, that maybe the forward model can give you some kind of an inductive bias, is actually showing up in these experiments. And as you increase the data to 100,000, the gap kind of disappears, and your inverse and forward model are performing, the joint and the inverse model are performing as well. Right? So this is, at least the simulation experiments show that, okay, whatever we kind of hypothesized is kind of holding true in this setup. Right? And now we can actually take this and try to test it on the real robot and see what happens with the real robot. Now, before I explain the results on the real robot, I'll just explain the baseline that we compare against, like as quickly as possible. In the baseline model, we start with the initial image and the goal image. And then we use an explicit object detector to detect the location of the centroids of these 2 objects. Given these 2 centroids, we infer what is the action that the robot needs to perform to get this image from over here to over here. So that is the baseline model, which assumes you have detection, and based on these, you can infer the poke. Okay. So now again, this is again showing the same results, but with the real object over here. So again, these are the sequence of images. And what you would see is the inverse model is shown in red, the joint model is in black, and the baseline is shown in blue. So both the models tend to perform better than baseline, and the joint model tends to perform better than the inverse model, even in the case of the real robot. Right, and this is showing the 3 different things: the first poke, the predicted poke, and the oracle. So if you compare the joint model between the first poke and the predicted poke, it seems that if you're doing this multi-step decision process, it is actually helpful even on the actual physical robot. Right?
Sorry, I have a question to the last area. So this center of, you poke center of mass, basically, right?
No, you poke anywhere on the object.
So what is this centroid that you said?
This is for the baseline model.
What's the baseline model?
And so you want to compare against, so you have an algorithm that you develop, and then you want to compare against, okay, some previous way of doing this, but the null model.
Oh, the null model is you poke the centroid.
So you poke the centroid in a way that will transform your initial image to your goal image,
Okay,
and you get this information. So what this is showing is that this is using all information about the object location, but nothing about the geometry of the object. Right? So the only way a learning system can do better is if it understands something more about the geometry of the object. Right? That will give it some information to kind of guide its poke in a better fashion. Right? So
Can we go back?
yeah.
In the hammer case, it looks like
Yeah, so for hammer, we have much more data now. And these plots are from May. So this is looking more and more like this. So these plots have to be up, and this also are improving. Yeah, so this is plots from May, which will be revised in a couple of weeks from now. So yeah. In this case, the amount of hammer data was around 5,000, and this data was around 20,000. So therefore, the learning was not so good in the hammer, at least when this figure was made. Right. So I'm going to skip this part slightly, and I'm just going to show one thing that instead of just doing rigid objects, we can also kind of manipulate deformable objects with this kind of a framework. Right? And for this, again, I don't think my thing will work. I'll just show one video and then end with that video, and then I can take more questions. So for that, cool. Okay. Right, so what we are doing in this work is that we want to teach a robot to manipulate like deformable objects such as a rope, right? And then the robot again collects its own data by kind of randomly like picking up the rope and then dropping the rope. And it does it again over a period of time. And this is just showing like the process of data collection. So it takes the rope, makes a poke, sees the next image, and then it keeps doing it. Right, so And so we have obtained around like 300 hours of this manipulation data. Again, like in the old framework, we train this system up, which can, given these two images, infer what is the poke or the action that you need to perform to transform these two things, right? So now this robot has learned a low-level model of how to manipulate the ropes. But now if I want to manipulate the rope in more complex forms, instead of trying to make the robot learn that, we actually use some kind of human guidance to learn that. The way that works is, maybe I'll just wait for the next thing to show up. So a human kind of demonstrates a formation of a complex pattern of rope. Right? So this is like the human is kind of specifying how to move the rope to kind of transform it into this complex shape. And then the robot starts with the first image and tries to go to this target image. So they're saying that, I learned a local dynamics model, but I don't know the high-level plan. So let the human specify the high-level plan, and then I use my low-level learned model to follow that plan, which is kind of similar like imitation, but there's no imitation learning happening over here. You're just kind of observing the human and then trying to copy what the human is doing. So that way you can kind of go to more complex shapes than you could. And so this is just showing that you can also kind of tie knots with this. So the human is just showing you a demonstration of knot tying. The robot takes these images as inputs and then tries to kind of do this process. So this is just like combining some kind of human performing a task with the inverse models that we have trained to kind of do more like complex.
So this imitation is done with one shot. I mean, you show the imitation, you show the human, and
Yeah.
this is right after.
Yeah,
There's
yeah.
No
No.
mistake.
And the thing is, you have learned the dynamics model, right? Because the human is showing you a sequence of images. And the learning is happened that you have image 1, image 2, what is the action that you need to perform? So the human is providing you a sequence of images. And then through your learning, which has happened over a period of time, you are able to infer the actions which can take you from image 1 to image 2. But there's no other learning in the imitation. And it has some like restrictions also, for example, so which are there. But in this setup, in the sense that the robot and the human workspace is exactly the same over here. Right? It's not that I'm watching a video from YouTube where you open the fridge and I'm able to copy that. So that generalization is not being shown in this video. But it's just showing if you have a simple model, then you can do more complex tasks by bringing human in the loop.
But they don't see exactly in your model, what is this image? I mean, there are a lot of freedom in imitation, right? So where is this?
So where is this happening is,
Yeah.
let's look at, Okay, so suppose consider this, right? So this is the initial rope. The human does this. You get image, you get image, you get image, right? So you get a sequence of images. And now you have a model which can say, given image 1 and image 2, what is the action I need to perform? So then you just perform that action from the sequence of images, and then you show how it looks like. Right? So it's not, there's doing no learning in imitation. The model has been learned. It's just copying what the human is doing over there. So I guess I'll just like stop here and not go more and more.
Thank you.
Cool. Yeah, and if you have any more questions, I'll be happy to take more questions.
So maybe just so I understand the focus. So could you go back to the picture of the joint model?
Oh, yeah.
And I know you said this a couple times, I just didn't quite get it yet. But
Yeah.
The joint model. So the left side was just turning the inverse model. So given one,
Yeah.
what was the action? Right?
Yeah.
And so why aren't you satisfied with that? Why isn't that?
Why not just take that framework and go?
Yeah, as work.
Oh,
I'm still talking.
I see. So the one thing which you hope to gain by that is that suppose if I now change my goal, right? Then I should be able to infer the sequence of optimal actions to go to that goal. And these inverse models are very local. Right? So now you want to do like long range planning where the objects shift significantly. In order to do that, you can't just collect data for like all possible long trajectories because the data collection becomes very sparse.
We just put the diagram up there.
Okay.
It's the joint model.
Yeah.
Like if you're given a target image really far away in time than your starting image, you couldn't use the inverse model.
Because
Okay.
yeah,
Is that it?
yeah, that is it. Yeah.
Good. Let me just.
Yeah. Yeah. I know.
Okay.
This one.
So with the left part only, then you could only do local,
Yeah.
like frame to frame things. But now, so why is it then? Tell me, why is it the right side going to help you do longer spans?
Because what you can do is you can say if I take this action, this is going to happen next, and if I take this action, this is going to happen next.
So you can feed in z-hats back into the action predictor and roll out.
So you can then do rollouts in the Z space. Maybe let me.
Oh, I can say I see. You can simulate that right side.
Yeah.
Then you can
Yeah.
loop it. I mean, iterate it.
You can loop it iteratively.
I see. But is that what did you show? That that's what it's doing?
So it's not doing that right now.
Oh, okay.
So this is what we are working on now.
I see. Okay.
So now how do you use this model to do this like planning over a sequence of actions?
Mm.
Right now you output one action, and that you can do because these images are not that far away.
Mm.
But if you want to now take images which are very far away, then you want to be able to infer a sequence of actions. This is exactly where this dynamics will come into play.
And why isn't then the right side? That's the right side. That seems pretty good. So why not just do that?
Oh, because then you are running into the issue of the nulls, like this, everything is reduces to zero.
Well, we have a solution to that.
Yeah.
Yeah, but-
So you can run like an optimization through the nested predictor, right? And say like, given an action, figure out the next z, right? So you do have z and z, like you still have the same amount of information, but you can use a single model instead of two models to do the entire process, right?
Like how come?
Because like, let's say you're given an action that you actually took to generate a particular z. So in the nested predictor, you can just regress that by saying, given this correct z and zt plus 1,
Yeah.
and then zt, optimize your model to predict the action, and then do an error on that.
So in order to do that, you have to learn your model somehow, right? In order to learn the model, you have to impose a cost on z. And so
You
you're
can
saying
still impose a cost on z in the same model there. It's
No,
still the same,
no, but if you suppose if you impose an L2 cost,
right?
then everything will reduce back to zero.
Yeah, but then it won't be able to predict the action correctly.
So this is exactly what this is doing, right? It's not
Right, I'm saying you can just do it in a single model instead of having two separate models.
So this is a single, and it is trained all jointly. When you look at it, it looks like it's two different models, but this is just like you get ZT, you have action coming, and you go to ZT plus 1.
Because your final gradient is being propagated in CT plus.
No, I'm saying you could, it's like sparse coding, right? You can infer the reconstruction not by using like a autoencoder, like a decoder model.
Just iteratively inferring.
Yeah, iteratively
Do
inferring.
gradient descent on
The actions.
on you.
Yeah.
Yeah.
Yeah, so you can also do that, and that works slightly worse in actually predicting
Oh.
the action.
Oh.
And the reason for this is because there are parts of action space which the network never sees in the training, and the gradient descent can find those parts of action space and make the model very confident.
Even that low dimensional?
Well, it
Still like
Regular.
continuous space.
it ends up happening, at least in the current system network. So we tried that, and that was the issue with that. That is why we stuck to just making the predictions in this setup.
And have you thought about, this is like very abstract and philosophical, but have you thought about thinking about image generation this way? You have this set of pixels, and you somehow want to, I mean, the action there is very abstract. It's not, it's in the world of images. You know, you're changing contrast, you're changing
Yeah.
lighting.
Yeah.
That's the action, quote
Yeah.
unquote. And you can parameterize those actions by just few parameters.
Yeah.
You know,
Yeah.
come from physics of the world,
Yeah.
and how you go from one image to another image.
Yeah.
You know what I mean?
Chelsea has paper for that, right?
Similar. Yeah, kind of. And yeah. And so
What's that paper?
I
So-
don't know the name of it.
not in this spread. So in that paper, what they do is they predict the optical flow,
Oh.
and then they copy the pixels to that. But that is what you're not referring to. What you're referring to is that if you train this thing by defining actions as contrast difference or defining them as
Yeah, I mean actions of that happens in the world that
Yeah.
changes images. I mean,
Yeah.
there are a lot of complex actions, but there are some
Simple
are very
actions.
simple. Lightning,
yeah.
you know,
So
the
there's
big one.
yeah, so one student is working on the camera transformations. Like if you move the camera around, this
Yeah.
is one more transformation that you can get. And then you can try to say, okay, I can predict this camera transformation, but in this space I can also say encoding plus camera gives you next encoding, and you can
Yeah,
use
it's
it as
very
a
cool actually.
Quackly
Yeah.
has a plot paper
What?
in that vein. Quackly
Yeah.
has a lot of papers in that vein where like given a transformation and the current image, what will the future image look like?
Hongla.
No, but in this
Oh,
framework,
okay, yeah, okay. Okay, sorry.
I mean, actually, the other
but
other
in
paper.
this framework, you know, I mean, the
It's a
the
very
magic
similar
in this
framework.
framework to me was, I mean, the key was going from action space expanding into high dimension. Isn't that was the magic, right?
That's not.
I mean, that's not, that was the key, the starting point.
No, I
mean,
think
that
I,
is- yeah.
no, I think that idea has been explored
Yeah.
in previous works also, that you want to expand the action into a high dimensional space.
No, what I mean is expanding action in terms of images. So you're changing lightings. I mean, let's study just lightings, right?
Yeah.
That's parameterized by, I don't know.
Yeah.
And then you just expand that to see how lighting can change images, you know?
Yeah. So I don't think anyone has tried that specific instantiation of
Wait.
things.
What about Tejas' work, like the one, the inverse graphics autoencoder? Don't they get latent variables in the autoencoder that actually gets like shape, shading, and reflective?
And it's a different instantiation, but yes, and they do get things. They explicitly feed in lighting
Right.
and the image.
This is like
And
the
try
black
to-
and white images and then
Yeah.
decoding.
Yeah.
So that and like Hongla as like Brian was saying, are probably like some two nice pieces of work.
Oh, I remember how that is. This was last year, right?
Oh,
Yeah.
Yeah.
So I guess the only difference is over here they were trying to reconstruct the image, and I'm trying to move away from reconstructing images. That's the only difference. Other than that, the frameworks are very similar.
Looking at tasks, that's this.
So you might want to look at this work of Becker and Hinton. You know what I'm
Okay.
talking about?
I don't think so.
So it's very related to what you're talking about here. They don't have actions, but the
Yeah.
idea is to say what they're doing in their paper is they maximize mutual information over space. They're
Okay.
saying, okay, I have my image pixels here and image pixels here.
Yeah.
And there's some property of these image pixels that are shared in common with these image pixels here. But
Yeah.
not pixel for pixel, not as a template. Like compute squared error, it's horrible, right?
Yeah. Yeah.
There's some property they share.
Yeah.
So for example, if it's a stereo pair,
Yeah.
then it's depth.
Yeah.
I have a
Oh,
left right
I
pair
know
here,
that
left
one,
right
yeah.
pair here, right?
It's a
Yeah.
nature paper.
And what they share is, yeah, exactly, they
Oh,
have
then
the
it's-
same
okay.
depth,
Yeah.
right? And so what they ask is, okay, what nonlinear function of
Can
these image
transfer.
pixels should I learn so that I have maximum mutual information between them? And
Yeah.
then it learns that
That-
it can be depth
that-
from
From pixels.
You've seen this paper.
Yeah,
I
I've seen
sent
this
it to you.
paper,
This is
yeah.
like, we did this like 2 years ago.
So it's a very good idea because so things they may not share that pixel per pixel level. That's not the right space to provide their common property. But
Yeah.
some abstraction of that, and then it says so a demonstration of an unsupervised way of doing that.
Yeah.
And then here, just assuming that these properties are shared across space, but they may be shared across time. That's the idea of
Yeah.
slow feature analysis.
Yeah. Yeah. Yeah.
Right, for learning variances.
Yeah.
and then here it's sort of like through, actions, when you act, and there's some property that you could predict about that, but it's not the pixels.
Yeah, so that would be, so I did one comparison against slow feature learning at least. Like if you train a slow feature learning based system and compare against predicting actions, the slow feature learning tends to do worse. But that is also, I guess, expected because there's a specific task that you're performing.
Well, depends on how you define the slowness over what.
Yeah, slowness over like a z.
Oh, I see. So square,
So you can define slowness over z and say z should vary slowly over time.
Oh, I see.
And you can then train that system up.
But that again also has a trivial solution, right? So you have to somehow.
So then you also say that frames which are far away should be like things which are not close in time should be delta far away. So that the distance has to be far away by a certain thing, and things which are close by should be close to each other.
In latent space.
In the latent space.
It's kind of hard to enforce.
And yeah.
Like you define some norms on some items.
Yeah, but the Hinton idea might be worth revisiting and seeing how it works.
And that's also kind of in the Karklin and Lewicki paper they talk about that that these, so some region of an image, the pixels here share some property of the pixels here, but what they share is their distributions.
Yeah.
They come from common distributions. It's not that they share in the pixel, so that they show that in their second layer that they can learn
the
representations that are, because it's a more abstract space.
Yeah.
Very cool.
So you optimize reactions, it would come up like crazy high. You could regularize that.
Yeah, there must be somebody to regularize the action space.
Yeah.
So, David Aaron